Thank you, Adrian. Good afternoon, everyone. My name's Warner Priest. I'm from Siemens, responsible for business development around the emerging technologies. And in particular, I'm going to talk about a case study that we undertook for the oil and gas industry just recently, and how it could be applicable in the mining sector. So let's see if this all works. So where are we today? If you look at that slide, amongst the 10 biggest challenges facing mankind, the World Economic Forum rates climate change, food security, and healthcare as 3 of its key concerns. The way we produce and consume our energy resources impacts all 3, which become more apparent through the slide as I go through. Did you know that we have about 21 days of diesel reserves in country? Disruption to our shipping lines could bring our economy to a halt in a very short period of time. Our energy security hangs in the balance. The growth in renewables over the last 10 years on average has grown by more than 30%. You can see that by those 2 graphs shown both in wind and solar over the last 10 years. In the same period, our global CO2 emissions have stagnated, but unfortunately still show a growth trajectory of about 1.5%. Going forward with the changes in legislation likely imposed globally, we can expect more renewable integration with a requirement to decarbonize more than just the electricity grid, but also the gas grid and transport and industry sectors. So what was this case study all about? Well, as I said, it relates to the oil and gas industry. It was in the Surat Basin. It's on a particular application that has been in service for a couple of years already. Siemens was tasked with undertaking a techno-economic assessment using our modeling tools as it related to coal seam gas extraction on the East Coast and how renewables could be employed through this process. The assessment was to compare CSG gas extraction and upstream processing using power from the grid with that of using renewables and gas engines and their own gas extracted as a fuel for power generation. It was quickly identified that the capital cost of battery storage in this particular instance, and I must say it's only for this particular plant, that the business case wasn't going to stack up, and rather to do more of a parasitic use of their own gas to drive engines was going to get this business case to work. Plus the use of our fisheye cloud forecasting solution for grid smoothing services as an alternative to the battery storage. So this is now putting fisheye forecasting cameras to monitor cloud cover and cloud movement rather than putting batteries in for grid stabilization. So this particular software that we use to do the techno-economic assessment, this is really where we start when we get involved in a project of this nature, is to work out, what's going to be the technical solution that makes sense from an economic point of view. And so we go through these various stages of working out what are the components that make up the generation, how are we going to integrate it into whatever network is required, and what are the economic drivers that are going to bring about value to our clients. And it's a software tool that we put in all the data, and then we get results in a number of scenarios out on the other side. The software tool used to be called Simpson. It's now called PSSDE. You may have heard of software called Homer. Ours used to be called Simpson. I don't know why. So this particular example, some of the financial data and inputs that we used, first of all, we needed to know the location. What was the irradiance in that particular area we import into our tool? What does the load look like, the single line diagram? How does that load run? What's the weighted average cost of capital, annual cost escalations, project lifespan. What does it cost them when they buy their electricity from the grid? And what will it cost them if they use their own gas? If they're selling that gas to market at $8 a gigajoule, we want that gas to go to market. We don't want them to be burning it to produce energy to extract their own gas. So that's really some of the data that we needed to work out what makes sense from an economic point of view. The grid was not too far away from the site. It was actually close by. So a 132 kV connection, $16 million, was cheap. So it was going to be a difficult one for us to get across the line, and this is probably why the battery didn't fit. The maximum power of this particular application was 30 megawatts, and the gas engines that we would deploy came in at a capital cost of $1,200 a kilowatt. So that is the load profile, and I must point out that load profile is shown and is characteristic of CSG, gas extraction, over a 20-year period. So within each year, the profile is pretty much constant. But as you can see, as we go from 5 years to 14 years to 20 years, that load profile changes. And that's characteristic of coal seam gas extraction. And that in itself also presented a challenge, because if you start embedding renewables, what do you start doing when the load starts to decrease? Below, we extract time series from Metanim to get the solar data. So that comes as data from a database where they collect information on irradiance. And we bring that in as data into our tool to work out what the irradiance levels are for that particular spot in Queensland. So once we've got that in, we've got all the data in, we run the model over a 20-year period. Running that model can take 18 hours, depending on how much data's in there, and obviously the processing power of the computer. You can see the result and the profile in the graph on your right. And you'll see there are 2 days there. The first day shows a lot of interference with cloud cover coming into play. And that doesn't work very well when you're relying a lot on solar. The second day, there's no cloud cover at all. We have about 10% spinning reserve running with the engines. But most of the power is derived from solar during that period of that day. So this is the result that comes out of our modeling tool. And the top graph indicates the levelized cost of energy for the different scenarios. So we look at the grid connect, that sort of purple color, is about 16.24 cents a kilowatt hour. If it was gas only, using gas engines to extract their gas, comes out at about $14.14 a kilowatt hour. And then if you look to the right, where we start to bring solar in, and at a capital cost from $1.60 a watt up to $1 a watt, to the right, 28 megawatts, $13.55 a kilowatt hour is starting to look pretty interesting, and is a better result than gas only. So that PV is now offsetting some of their costs associated with their use of gas. The chart below is the capital cost, and you can see the more PV we put in, the higher the capital cost. But throughout the whole calculation, it's really that levelized cost of energy, taking the capex cost into account, that we now can produce energy and extract that gas at a lower levelized cost of energy using those gas engines. So what's the sky camera about? As I say, we couldn't get the numbers to work with the battery storage because of the capital cost associated with this. These sky cameras cost about $1,000 each. And all they're doing is, it's a fisheye sky camera. It's looking at the sky and it's looking for clouds. When it's clear, we're running off solar. When we see clouds coming and we can forecast them coming, then what we start to do is curtail our solar and the gas engines start to ramp up. And we always keep a constant 10% spinning reserve with our engines, even when it's a fully sunny day. So the idea is that we avoid the battery using the sky camera through that process. So that green line, that green box, we'd be running on solar only, and where you see those little interferences, which are clouds, we would be running on gas engines during that period. So a simple use case shown here, and hopefully you can digest what's written here. If we've got two gas engines, 300 kilowatts each, and they're running 24/7, and we've got some PV there, we're going to have to curtail that PV. And we're probably going to run those gas engines at about 40 to 60% loaded, and we heard from the previous discussion that those engines don't like to run partially loaded. Their sweet spot is sitting at about 80 to 90% loaded. So what we want to do is we want to switch off one of those gas engines, only have one gas engine running at its peak load, and bring in as much of that PV as possible. And with a sky camera, seeing that the sky is clear, we can do that. And if we see the clouds coming and we can forecast it, then we can curtail the solar and get both engines back up and running. And that would result at about an up to 8% saving on fuel. So this gives you a bit of an idea as to how this all works. The image on the left is the image that comes out of the sky camera. We then take that image and we flatten it, and then we apply our artificial intelligence and image processing engine, and we can work out now what the exact irradiance is. The black line that you see in the graph below is now, and you can now see the movement of the red line coming towards us, which is the forecast that something is going to happen. Clouds are going to come over and disrupt our solar. And the blue is the actual irradiance that will happen. So we can now begin to see cloud cover coming. It's about to hit us. Curtail solar, engines start up, and boom, we're covered. And everything's running smoothly. So it's a grid smoothing service using a low-cost camera with special algorithms and artificial intelligence behind it. So that over there is the setup. It's essentially this low-cost camera. We also have a photocell or an irradiance measurement device if required, obviously on the a slightly more expensive device. But I mean, that total system would be about $10,000. We have our forecasting software, industrial PC, and the associated logics and into the power system controller. That actual camera doesn't exist anymore, unfortunately. It got taken out by Hurricane Maria in Puerto Rico last year in September. So no camera, but we got about 2 or 3 years worth of good data in that application in Puerto Rico. So what happens now when we get to the point where our load starts to decrease on this particular coal seam gas plant? At about year 14, we've got about 10 megawatts of curtailed PV coming into the system. It's being thrown away because their load has now changed. They've got through their peak. This is where we now potentially introduce an electrolyzer into play. And so a 10 megawatt electrolyzer, which is our new Electrolyzer 300 platform, plug that in. As part of these CSG gas processing plants, there's wastewater. We now direct that wastewater into our electrolyzer, and we use that. We absorb what will be curtailed energy, wasted energy, into those electrolyzers. And so now what we're doing is we're producing 100% pure hydrogen, 100% pure oxygen. And we can take that hydrogen and we can start to inject it into their existing gas networks to port, and then they can start to market an LNG that's got a little bit of a green tinge to it, which might have a little bit more value. So you may ask, what are the numbers, and will that make sense? And so there are three graphs here. The first graph shows the capital cost of the electrolyzers sitting at about $1,500 a kilowatt. So a 10 megawatt unit would be about $15 million. And we've got a couple of lines there. We've got the top line, which is red, which shows renewables coming in over a full load hours of anything from 500 to 8,000 hours in a year. So where you've got that complementary wind and solar coming in, and you can do 6,000 to 5,000 hours. On that red line, you're probably looking at making hydrogen about $7 to $8 a kilogram. Well, $7 a kilogram. The lower line is the good renewables and complementary wind and solar that we have. That's that greenish line here in Australia at that $1,500 per kilowatt for the electrolyzer. And the blue line shows it where the all you've got is your capex cost. So your input cost of energy is spilled energy. It's wasted energy that you typically throw away, which is what applies to this particular project. Because that's 10 megawatts of energy on that CSG plant after 14 years that they're going to throw away. So that's wasted energy. The green line shows the energy input at $40 a megawatt hour, and the red at $80 a megawatt hour, and we're probably somewhere between that in certain parts of the country. If the capex cost of those electrolyzers come down to 1,200 kilowatts an hour, then we can start to see where we can produce the hydrogen for. And with natural gas at $8 a gigajoule, the hydrogen equivalent value needs to be produced at about $1 per kilogram. And that's not going to be easy to achieve. But as we start to get down to a capital cost of those electrolyzers sitting at 600 kilowatts, then we're starting to see that with spilled energy, we can be making hydrogen at about $1 a kilogram. And I reckon that we will be there in about 10 years' time. Taking into account that at $8 a kilogram today, our gas prices are likely to be sitting at about $15 a kilogram in 10 years' time, if not higher. So that's starting to make an interesting business case as far as hydrogen is concerned, especially if you're trying to displace diesel, both for your power generation and your transport on your mining operations. So a couple of examples. Siemens delivered this first project in 2015, so it's been running for some time. It's about a 5 megawatt electrolyzer. It's got a wind farm attached to it. It injects the gas into the grid. They use hydrogen to make glass, and they take it around to dispensing stations for fuel cell vehicles. This particular plant is the world's largest, that was commissioned in Hamburg in Germany. They make lipsticks from the hydrogen, so it is green lipstick. It's actually red, but it's got a bit of green tinge to it. They are that particular one, I think, it's a 5 megawatt at the moment, and we're at the moment putting in a large one for a steel plant in Austria, which will be 6 megawatts, which will also be, again, the next biggest one. So some interesting projects on the go there. There's been a lot happening here in Australia. Our first project is going into the ACT. In fact, the electrolyzers have been sitting in our workshop for almost a year now, waiting to be delivered into Canberra. They're still trying to find a site where they want to locate it. And that was in partnership with Hyundai and Newen. and the ACT government. The next one is going into Tonsley Park. It's going into a microgrid in South Australia, and that will be gas injection. AGIG are experimenting with this gas, and then that hydrogen will be essentially directed to transport, because this is where you're going to get the biggest bang for buck at about $12 to $15 a kilogram going into a car. But we have this chicken and egg problem, and so AGIG are looking with government to help solve that particular issue that we're in right now. This is this is the Tonsley Park one, sorry, and we recently completed a study with the Advision and the South Australian government on their hydrogen roadmap, which went very well, and as a result, the Tonsley Park project's come about, and there are now talks about the biggest PEM electrolyzer project that could go ahead in Australia at about 50 megawatts in size on a solar wind farm, and you may have seen a bit of news. Hopefully that'll go ahead. That really will put Australia on the map, because we as Australia have a unique opportunity. We've got an abundant amount of renewables. We've got a very large landmass. We've got a very small population. We're good at digging stuff out of the ground, like gas, like minerals, and exporting it. We have an opportunity to to export our wind and our sunshine to markets like Japan, Korea, and start to decarbonize the rest of the world. So thank you very much for your attention, and I hope that was interesting.